Okay, so for our final extravaganza into geometric sequences and all the fun that is that, we've got our sum to infinity. Now, formula is, shall I add you a little formula list over here? The sum to infinity is equal to term 1 over 1 minus r. This looks a little bit like our sum formula, the other variant, maybe more so, but not quite that. So what this means is that we can sum some expressions to infinity. What's important here is that the absolute value of r must be less than 1. Can't be equal to 1, can't be more than 1. So let's imagine a couple of sequences for a second. Imagine this one, 2, 6, our favourite, 54. If we sum the first infinite terms of this, it's going to be ginormous. Like this is growing and growing and growing, it's going to be huge. But take another one for example. 2, but this time with a halving factor. 1, a half, a quarter, an eighth, etc., etc. If I sum this, hopefully you can see that S1, the sum of the first term, is 2. S2, the sum of the first two terms, these two, is 3. S3, the sum of the first three terms, these ones, is equal to 3 and a half. S4, the sum of the first four terms, is equal to 3 3/4. Stop the video now if you want to check the maths on that. I'm just adding these terms up. S5, the sum of the first 5, is equal to 3 7/8. S10 is equal to 3, and I'm going to say 255 over 256, but I could be slightly out there. But the point is here, it never gets to 4. It's never equal to 4. This is called a limiting value, and that's the upper bound of this sum. And in fact, so upper bound that it never quite gets there. In terms of graphs and relations that you've been doing in this topic, in this unit as well, 4 is like an asymptote on the graph for this exponential function. So we'll get to sketching exponentials and talk a bit more about asymptotes again. We test our formula here. T1 is 2 and r is a half. We get 2 divided by 1 minus a half, which of course is equal to 2 divided by a half, which is equal to 2 times 2, which is 4. So we get that sum to infinity is 4, the upper bound of our sums. What I'm going to do now is show you where it comes from, and then we'll leave it there. Okay, so let's talk a bit about where the sum to infinity comes from. So we have this rule, sum n equals T1, 1 minus r to the n, over 1 minus r. Now I'll just make, it'll work for this as well. We'll just end up with some pesky negatives we've got to deal with, but it will work. Maybe it's a worthwhile exercise for you. So sum n, I'm going to go, well, what is sum infinity? And keep in mind that I'm dealing with only the modulus or the absolute value of r is less than 1. So I'm saying r is between -1 and 1 and not equal to, because remember, if r is 1, boring, it's a boring sequence. Anyway, sum to infinity is equal to T1 times 1 minus r to infinity over 1 minus r. So here's a little thought experiment for you. If r is, I don't know, let's say r is equal to 0.2, what's 0.2 to the power of infinity? Hopefully you can see that this just gets smaller and smaller. You can get your calculator if you want. Smaller and smaller and smaller and smaller and smaller. Basically, it equals 0. So what about if r is a bit bigger? Like we said, less than 1. So what if r is 0.999? And now again we're talking to the power of infinity. So I should put r to the power of infinity here. That's better. Then what happens there? Well, it turns out that's actually equal to 0 as well. It does go towards 0 slightly slower than this one, but it still goes towards 0 eventually, and infinity, it's a big number. So, no matter what, if r is less than 1, then that value to the power of infinity is 0. So it means that we can cross this out and put a 0 here. And that gives us term 1 over 1 minus r. And that's all we need to do. And this will give us our limiting sum, or our sum to infinity for any sequence, as long as r is less than 1, and the absolute value of r is less than 1. Now a couple of things about how this looks. A geometric sequence that is growing, and I'm not going to deal with oscillating ones now, but oscillating bounces back and forward. R can be -1/2 and we can still have a limiting sequence, so it works. But I'm just going to deal with one that's growing. term 1 is here, term 2 is here, term 3 is here, here. Okay, that's happening. If I add those values together, it just keeps on going. But if I've got one that's decaying, so let's say I grab this pink pen here, and the first term is here, but then the next term is halfway down, next term is halfway that, so it's decaying and getting towards this asymptote. Well, in this case, we get, now remember this is kind of discrete data, we're talking term 1, term 2, there's no term 1.5, so I shouldn't really connect them, but I'm going to do it anyway, just to show you the pattern. Okay, if I add these together, that plus this is here, 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 a little bit higher again, a little bit higher again, but what I get is this, and it limits to this asymptote, and that asymptote is our sum to infinity, our limiting value. So there you have some information about sum to infinity, very theoretical. I go and dig into the examples you have from class and the work that you're doing. That'll give you all those specific cases. But for now, this gives you a really general overview on what's happening. And of course, our important rules. All the best.